Welcome to the Fundamentals lecture for Chem 117 Experiment 4. This week we'll be talking about liquid-liquid extraction. Now specifically we're going to talk about liquid-liquid partitioning and what happens when we have two immiscible solvents that are competing to dissolve a non-volatile organic compound. And once we figured that out, we're going to ask ourselves, how does the pH of an aqueous layer in one of these systems alter the solubilities and therefore the partitioning coefficients of those compounds? We'll talk a little bit about how we can design liquid-liquid extractions intelligently, knowing how pH affects or should affect the solubility of organic compounds in water. Then we'll talk a little bit about some practical aspects of how extractions are conducted in the lab and why we use the techniques that we do. We've got a lot to cover, so let's get started. Let's begin by considering a situation in which we have two immiscible liquids, usually an organic and an aqueous. Now, if I add my water to the beaker here, I get my aqueous phase solution. Of course, I have to put a solute in there. So let's put in a solute that's very polar, meaning that it makes good, strong intermolecular interactions with the water molecules in that aqueous phase. Now I'm going to pour on top of that an organic solvent, something like ether or benzene, which will not mix with the aqueous phase because they are what we call immiscible, which is a term that we use in chemistry to describe liquids that don't dissolve into one another well. Now what's going to happen when I expose my high polarity solute in aqueous solution to an organic phase like the one I've just put here? Well, what's going to happen is a dynamic equilibrium will establish itself, in which my high polarity solute distributes itself across the two phases. But notice that it doesn't distribute itself evenly, that it prefers the aqueous phase more than the organic phase because of its high polarity, and so it has a greater residence time in the aqueous phase, meaning it's preferentially accumulated there. Now let's turn our attention to the second beaker. This time I'm going to use an aqueous solution containing a low polarity solute. And again, I'm going to add my organic phase to the top here and allow equilibrium to establish itself. But because my solute in this case is lower in polarity, it has less of an affinity for being dissolved in the aqueous phase and actually prefers the organic phase. So now that the dynamic equilibria are established, we can clearly see a difference here, that one of my compounds, the high polarity one, has accumulated in the aqueous phase, while the other has accumulated in the organic phase. This is the phenomenon on which we're going to base our separation technique. We can essentially separate compounds based upon their relative affinities for one of the two phases. Sounds an awful lot like something we discussed previously, doesn't it? When we use two liquid phases which are immiscible with one another, as opposed to, say, a solid and a liquid where one can be stationary and the other mobile, we use a different name to refer to the technique. We call it a liquid-liquid extraction. It's essentially a technique in which two immiscible liquids are used to isolate compounds from one another based on their solubilities. Because the solvents partition or distribute themselves between those phases, we can mathematically model exactly how much accumulates in each layer using an equilibrium constant, which we call the partitioning coefficient. So in this case, a partitioning coefficient is simply an equilibrium constant for the concentration in one solute and the concentration in one solution and the concentration in another. So on the left-hand side, my high polarity compound, if I define Kp, or the partitioning coefficient, as its concentration in the organic over its concentration in the aqueous phase, I expect that its partitioning coefficient will be relatively low because the denominator is the larger of the two numbers. Whereas, in the case of my low polarity compound, if I define Kp as the organic over aqueous, I find that the number is much larger. So what we're looking at here is a situation where differences in the partitioning coefficient correlate to differences in solubility in the two different immiscible layers. In other words, the more different the partitioning coefficients are, the more easily I can separate one compound from another because they're behaving differently. So if I have a mixture of my low polarity and high polarity compounds and I want to separate them from one another in space, I can take an aqueous phase solution of the two and add an organic phase. And remembering from our previous discussion that they choose to or tend to partition into different layers in this system, all I have to do is wait for equilibrium to establish itself. And I should reach a situation in which my low polarity solute has partitioned into the organic phase preferentially, and my high polarity solute into the aqueous phase. Now, if I'd like to collect one or the other, it's as simple as collecting the appropriate phase. Now let's move on from our generic compounds of high polarity and low polarity and start talking about real organic compounds. Let's take the example of phenol. And let's talk about how phenol partitions between water and benzene. Now I can determine its partitioning coefficient, and I don't have to run a single experiment. All I need to do is go to a data table and a reliable source and locate the maximum solubilities of phenol in the two solvents. In this case, phenol's solubility in benzene is 8.83 grams per liter, and in water it's 6.67 grams per liter. And I can use these numbers to calculate its partitioning coefficient as 1.25. And I can use that number to predict the outcome or the distribution of phenol in any concentration that I choose. For example, let's suppose we have 1 gram of phenol dissolved in 250 milliliters of water. I'd like to know, if I add an equal volume of benzene to that and allow equilibrium to establish itself, how much phenol can I expect to be in the benzene layer? Well, knowing that Kp is 1.25, and knowing that the amount which moves out of the water, x grams, must be equal to the amount which accumulates in the benzene. So this gives me a single equation with one unknown, which I can solve using some high school algebra, and discover that 0.56 grams of my original 1 gram of phenol has moved into the benzene layer. So I can use the partitioning coefficient to predict where I'm going to find most of my phenol at the end of this process. But is that all there is? Am I at the mercy of this partitioning coefficient when it comes to moving phenol back and forth between benzene and water? Well, the answer to this question is no, I'm not restricted by that partitioning coefficient. And the reason is phenol is a weak acid, and it can be deprotonated in sufficiently basic aqueous solutions. So while I determined my partitioning coefficient to be 1.25 when we're dealing with neutral phenol, as we are on the left side of the slide here, if instead I'm using an aqueous base that is sufficiently strong, my equilibrium is no longer neutral phenol and benzene versus neutral phenol and water. My equilibrium is now neutral phenol and benzene versus charged phenolate anions in the aqueous layer. And as you might imagine, phenolate being charged is far more soluble in water than phenol itself. So I can manipulate the partitioning coefficient if I make my aqueous layer of the appropriate basic pH in this case. But this begs the question, just how basic does it have to be? Let's say I want to get 99% of the dissolved phenol in my aqueous layer to be charged phenolate. This would, within reasonability, maximize its solubility in the aqueous layer. Just how far do I have to go to make that happen? The answer to this question regarding pH and solubility lies in a familiar equation from general chemistry, the Henderson-Hasselbalch equation. I'm going to demonstrate this using a chemical cousin of phenol known as 2-naphthol, which has fairly similar chemical properties, including a pKa of about 10. The Henderson-Hasselbalch equation is essentially a rearranged acid dissociation constant, which gives me the relationships among the pKa of a compound, the pH of the solution in which it's dissolved, and the logarithm of the ratio of concentrations of conjugate acid and base, only one of which in this case is ionized. So if I plot the Henderson-Hasselbalch plot for 2-naphthol, I get something like this. A situation in which I have 0% ionized at low pH, which would be where the conjugate acid is dominant, and 100% ionized at very high pHs, where the conjugate base is what's dissolving in water. Now, if I were to take an aqueous solution of about, say, pH 6, I can only dissolve a very small amount of naphthol in that, because it will be dissolving as neutral naphthol, which is got a little bit of polar bond there, but it's essentially very low polarity and is also uncharged. But if I change the pH of that aqueous layer to something very basic, like let's say 14, now I'm dealing with not dissolved naphthol, but dissolved naphthalate ions. And that means the solubility is drastically increased because the ion-dipole interactions between the naphthalate and the water are much stronger. Notice that our relationship tells us from the Henderson-Hasselbalch equation that for every unit of pH that we change a tenfold amount of how much is deprotonated. So it only takes a few pH units above or below the pKa of a compound to maximize this effect. And to reach our 99% benchmark, we need to go 2 pH units. So at pHs of 12 and beyond, we can think of it as being dissolved only as naphthalate, and at pHs of 8 and below as being dissolved only as neutral naphthol. So how does this adjusting the pH to alter aqueous solubility impact the outcome of liquid-liquid extractions? Well, let's begin by thinking just about naphthol, but this time instead of in only water, it now has a second phase that it can partition into in the form of some kind of organic. Remember, my Henderson-Hasselbalch plot tells me that at pHs of 8 and below, I'm dealing with naphthol dissolved in water, but at pHs of 12 and above, I'm dealing with naphthalate. Now let's take a look at what goes on in this interface between our two solvents as we change the aqueous layer pH. At pHs less than 8, we have a situation where the equilibrium is that between neutral naphthol in the organic and neutral naphthol in the water, meaning that it's going to prefer to be in the organic phase, and only a small amount will dissolve into the water. But as I change the pH of the aqueous layer, again moving up to something like 12, 13, or 14, now I'm dealing with dissolved naphthalate, whose concentration is much greater, and therefore I expect more of the naphthol to partition into the aqueous layer. So I can alter the pH of my aqueous layer as a means of determining or directing my naphthol from one phase to the other, depending upon my needs. Now let's consider how we can use this behavior and our ability to manipulate where these compounds accumulate to do a separation. Let's take a look at 3 compounds. First, let's look at naphthoic acid, which is chemically very similar to naphthol, except that it has a pKa of about 4 as opposed to 10. So its Henderson-Hasselbalch plot will look something like this, with its breakpoint at around pH 4. We've already seen how naphthol will have a Henderson-Hasselbalch plot, which has a breaking point somewhere around 10. A third compound to consider in a different situation would be a compound like naphthylamine. Now notice that naphthylamine is actually a base, so it's charged at lower pHs as opposed to at higher pHs. So its Henderson-Hasselbalch plot will be turned on its head, as it were, with the greatest percent ionized at lower pHs. And its breakpoint is determined by the pKa of naphthylammonium, which is about 4.6. So how can I use these Henderson-Hasselbalch plots to graphically guide my decision on aqueous layer pHs to optimize extractions? Now let's consider our 2 weak acids and how we can separate them, or at least design a separation, using liquid-liquid extraction. Let's say we have 2 different phases in a separatory funnel, the device pictured on the right here. And we'll talk a little bit more about the device itself later. What we're interested in right now is, depending upon the pH of the aqueous layer, what goes on at this interface between the two? Where are we going to find most of these compounds? Well, we can overlay their Henderson-Hasselbalch plots and immediately see that there are some similarities and some differences. Let's begin at a very low pH. Let's say that I have an organic layer above an aqueous layer with a pH of 2. This puts me down here in the Henderson-Hasselbalch plot, in a region where neither one of them is substantially ionized when they're in the aqueous layer. So I expect them to preferentially accumulate in the organic layer, because we're dealing with the solubilities of these neutral compounds, and they don't like to go into water when they're neutral. But if I change that pH to 7, there's a huge difference between their percentage ionized, meaning that I expect my naphthoic acid to move into the aqueous layer as naphthoate anion. At this point, if I were to separate my two immiscible phases, I would be affecting a separation of the two compounds. But if I continue and raise the pH even higher in the aqueous layer, let's say that I go to pH 12, now I'm in a situation where both compounds dissolve in water as ions, and that means that the naphthol is also very soluble in water and therefore will partition into that layer. So separating my phases at this pH also would not affect the separation of my compounds. So the key here is to find the greatest difference in the Henderson-Hasselbalch plots for your two compounds, and use that as the pH of your aqueous phase in order to direct one compound into the water and keep another one in the organic. Now let's take a look at what happens when we're dealing with acids and bases. Remember that naphthylammonium and naphthylamine are a bit different because in this case we have the charged species in the lower pH region of our plot. So the Henderson-Hasselbalch plots for these two compounds look something like this. So you can see what's going on here. Now, as opposed to having the greatest difference at moderate pHs, we get a very large difference in the percent ionized at low pH. In this case, that's going to favor our basic compound, the naphthylamine, accumulating in the aqueous layer. But if we raise that pH to 7, which worked great for us last time, we run into a problem because now they have very similar water solubilities, and that means we're not going to have a very good separation. In this case, both of them will accumulate in the organic layer more because they're not charged when they're dissolved in water at this pH. Continuing on further to another extreme, at very high pHs, my naphthol is expected to migrate into the aqueous layer because it's dissolved as naphtholate. So we can see here one benefit and one drawback to separating organic acids and bases. The benefit being that we get to pick which layer each one moves into, but the drawback being that we have to use very strong acids and bases to accomplish it. Now it's time to talk a little bit about the practical aspects of liquid-liquid extraction. Now, we accomplish liquid-liquid extractions using a device known as a separatory funnel, which is this gadget down here, which is sort of a conical shaped device with a Teflon stopcock at the base and an opening at the top through which we can add different solvents and different compounds. The first thing I want to point out here is that we never clamp one of these devices using 2 or 3 fingered clamps. They're simply not stable enough. Instead, we use a metal ring clamped to the rail that's just a little bit narrower than the top of the flask. So when it's inserted and lowered downward, it eventually stops and is held in place by that ring. Now, to begin the process of conducting a liquid-liquid extraction, we load a solution into a separatory funnel supported by a ring. We simply pour our solutions and solvents in through the top, being sure that, of course, the stopcock at the base is closed at the time so that everything stays inside. The next step is to agitate. We agitate to speed up the rate at which the equilibrium is established, to be sure that we get the proper distribution of compounds across the two phases. And this is done by placing a stopper in the opening of the separatory funnel and then inverting it back and forth several times over the course of a minute or two. Periodically, we want to be sure that we vent our separatory funnel to prevent pressure building up from either solvent vapors or byproducts of the process of the partitioning. This is done by inverting the separatory funnel, being sure that you hold the stopper in place with your finger, and then with the top vent pointed back into the fume hood, we open the stopcock, and this releases the pressure. The stopcock is then closed, and agitation can continue. Once we're confident that equilibrium has been reached, we allow those two phases to separate once again by returning the separatory funnel to the iron ring and allowing gravity to cause our two immiscible phases to separate based on their densities. Now, occasionally we get what's known as an emulsion, which is where very small droplets of one solvent and the other become sort of metastable and don't really want to separate well. And when this happens, we can usually break up an emulsion by very gentle agitation with a glass stir rod. Once the phases have completely separated, we isolate them from one another in space by opening the stopcock, being absolutely sure that the stopper is removed, and then allowing the lower of the two phases to drain out of the separatory funnel into a collection flask or beaker. At this point, we should have physically separated our compounds in space using liquid-liquid extraction. So why do we go to the trouble of agitating during an extraction process? And why is it so important that we do it? The reason is this: we want to reach equilibrium as quickly as possible. We're relying on equilibrium constants to predict the outcome of an extraction, so we have to be sure the system really is at equilibrium before we begin separating one layer from the other. Now imagine two different immiscible liquids in a separatory funnel at rest. The only surface area contact is that very thin interface between the two solvents. So in order for a compound to migrate from one to the other, it has to find its way to that interface. And with a bunch of molecules taking random walks through the solution, this can take a very, very long time. But by agitating sufficiently, we create small inclusions of one solvent in the other. And this means that there's a tremendous amount of surface area contact. So molecules have much greater opportunity to partition from one phase to the other, thereby reaching the equilibrium much faster. So when we do agitation, you want to be sure that you're creating these small inclusions of one solvent in the other. If agitation is too gentle, it won't accomplish anything. If agitation is too vigorous, you run the risk of creating an emulsion. So getting just the right amount of agitation is actually a very important skill to hone to be sure that your liquid-liquid extractions always turn out the way you expect. So another logical question comes up here. If I'm creating these inclusions of one solvent in the other and really shaking things up during the agitation process, how do I know which solvent is the one on top and which is the one on the bottom after I'm done and the phase separation process begins? Now the answer is we use something called a water drop test to be absolutely sure. Typically, non-halogenated solvents like diethyl ether, toluene, and benzene can be expected to be the top layer in a liquid-liquid extraction because their densities are less than that of water. Halogenated solvents, on the other hand, like dichloromethane and chloroform, have densities that are substantially greater than that of water, and therefore they usually accumulate as the lower layer. But there's a catch there. We're dealing here with the densities of solvents. But what really dictates the behavior is the density of the solution. And a solution with a large amount of very high mass solute might defy prediction here. So we need a test that will absolutely let us know which layer is which. For this, we use what's called a water drop test, in which we add a drop of water through the top of the separatory funnel. And depending upon what we observe, we will know whether that top layer is aqueous or organic, because water should mix well with aqueous solutions, but not well at all with organic solutions. So think about what you expect to observe in different situations and be ready to discuss that when you come for recitation. This is a big gotcha in the lab. You've got to know which layer is which, because if you don't, you may end up collecting the wrong layer and throwing your compound into the chemical waste. So, water drop test every time to be sure. I'd also like to mention that the stopcocks that are used in our separatory funnels are made of Teflon, which is a fantastic material for liquid applications because it requires no lubrication. So when we use a Teflon stopcock, we don't have to add grease to a joint, and that means that liquids draining through and over the stopcock don't become contaminated with those greases. The problem is that they're very easily damaged because of how soft they are. So at the end of the day, be sure that A, you don't scratch it, and B, that you don't leave your stopcock tightened into your separatory funnel receiver very tightly, because the pressure may actually cause the Teflon to deform over time. So be sure that you store the stopcocks loosely threaded into the corresponding glassware and not tightly threaded on where they might get deformed. So now that we've covered how and why partitioning of organic compounds happens between two immiscible liquid phases and the effect that pH can have on that, in the lab this week we're going to try to determine the partitioning coefficient for two different compounds in two different systems. Our goals will be to measure the partitioning coefficients of 2-naphthol and benzoic acid when washed with two different pH aqueous solutions. So you will have one of these two compounds assigned to you and your partner will have the other, and you will determine their partitioning coefficients in two different systems. Then you're going to use that information to determine the optimal aqueous phase pH for an extraction experiment and propose how you would accomplish a separation of one from the other if you needed to do so. We'll see you in the lab to collect that data later this week.